Good afternoon, everyone. Thank you for joining the presentation. My name is Tohidul Islam. I'm a PhD candidate at University at Buffalo, and I'm excited to share my research on progressive learning for multi-component materials design. So this work focuses on machine learning side of a larger materials design project. My main role was to develop tools and methods that can be integrated across different parts of the project. And these tools are designed to work across like multiple material system and length scales. So we start with the concept of materials design tetrahedron. So we are introducing this concept where there are four main key areas in this design. Those are chemistry, structure, processing, and properties. So in my work, I use this concept across like different length scale. For example, we look at how chemical composition and electronic structure affect microstructure and mechanical properties. And then we use machine learning as the central tool to connect these areas and handle large scale compositional space and multi-physics complexities, and also learn nonlinear correlations and enable property predictions, for example, yield strength and ductility prediction for high entropy alloys. And in this slide, I show the main framework of my research. So we are trying to learn patterns at multiple length scales. For example, from quantum scale to microstructure and up to device scale. And there are four main pathways, as you can see in the figure. And each pathway shows how we use the data and machine learning for a specific relationship. And for today's presentation, I will focus on two of these case studies. And due to the time limits, I'll cover only two of these case studies. And going to the first case study, which is about electronic structure and how they relate to mechanical behavior. We started with the idea that electronic configuration might contain useful information about how atoms bond and how materials deform. And the goal was to see if we can use electronic configurational data, for example, density of states, as feature to predict mechanical properties. So the objective is simple here. Can we predict stacking fault energy based on the density of states? So, and in the methodology, as you can see, we start with a data set that has density of states of single elements. And we applied dimensionality reduction techniques, for example, principal component analysis or UMAP, and reduce the dimensionality of the density of states into two-dimensional or three-dimensional feature space. And then use the machine learning to learn how this feature correlates with stacking fault energy. And the figure on the left side is that shows how elements are positioned in reduced dimensional space based on their electronic configurations. So let's say two elements, if they're close together, meaning their density of states patterns are very similar. In contrary, if they are far apart, for example, copper and zinc, they are positioned in different positions. So we can say their electronic structure are very different, and this can help us in designing of materials and alloys. For example, if we want to add zinc into copper and create the traditional alloys, for example, brass, with certain stacking fault energy. So someone may expect that adding zinc into copper may enhance the stacking fault energy in the alloy. But in reality, the opposite happens. And we know from the figure why. This is because their electronic configuration are very different compared to each other. And the figure on the right side, it shows our predictions and connecting to different length scale from electronic configuration to microstructural property like stacking fault energy. And we want further to test our model on more complex system. So we solely train our model on single elements, and we want to expand this model to predict stacking fault energy of alloys. As you can see here, the blue points, those are copper and zinc alloy, namely alpha, beta, and gamma brasses. And you can see here that our predicted stacking fault energy are very close agreement with the actual experimental stacking fault energy. And it correctly predicts the stacking fault energy of these binary alloys. And this confirms that our model is not just fitting the noises, it also learning the physical pattern in the data. It also means we can now design new alloys by selecting elements and based on their density of states. We also found that changing a small amount in chemistry, as you can see in the figure on the right side, that we are changing zinc fraction in the copper zinc alloy, and their stacking fault energy changing with the zinc fraction. And it can be very useful tool for the microstructural engineering where we want to design material with certain stacking fault energy value. And in the next, we want to take this approach into further. Now, can we make the material system more complex? For example, we trained our model into single elements. We expanded it into binary alloys. Now we want to predict property of a more complex system, which is high entropy alloy. So the question, if we can predict microstructural property like stacking fault energy from density of states, can we also predict mechanical properties like yield strength and plasticity? I must remind you, this is more complex problem because these properties depend many more factors, and especially in high entropy alloy where many elements interact at the same time. And they usually follow a trade-off in properties. For example, if we increase the strength, their plasticity goes down. So we wanted to find compositions that can break this trade-off and see if our density of state approach can help in this regard. Here we are comparing two different sets of models. As you can see, the figure on the right side, B and D, those are solely trained on chemical information data, and the other A and C, that is trained on density of states on top of like chemical information. And you can see that our prediction accuracy increased from 73% to 90% on prediction of the yield strength when we added electronic configurational data into the model. So we found that adding density of states that improved our prediction accuracy. And this means our model is now learning more detailed information and that is related to bonding through density of states. So this also supports our idea that initially we assumed that energy dependent density of states, those carry hidden patterns that are related to atomic bonding and strength and plasticity behavior in materials. In this slide, we analyze the influence of individual element onto properties, for example, yield strength and plasticity. And we found that molybdenum that enhances yield strength and reduces plasticity. Also found that vanadium that promotes plasticity in the alloy. This is important because now we can design alloys by tuning the molybdenum and vanadium balance and their ratios in the alloy. And the figure on the right side, we have three experimental alloys. that can be used as a support of our findings that we found in the figure on the left. The alloy in the middle, let's say we are increasing vanadium and reducing molybdenum in percentages. And as you can see, there is a drop of 7% in strength due to increase in vanadium and reduction in molybdenum. Also 60% increase, it's a big jump in plasticity. And the other alloy that is where molybdenum and vanadium both are reduced, and you see the 10% plasticity reduced and yield strength increased by 9%. So moving on to our second case study, this one focuses on connecting chemistry and processing parameter at the same time to property and microstructural behavior. So we wanted to build a model that learns this relationship and predict mechanical properties based on chemical composition and processing parameters. And the goal is to predict properties like yield strength and hardness, plasticity, and using both elemental composition and processing parameters. And most of the previous studies that treat these two separately, either focusing on chemistry or processing, but in this data-driven study, we combine them in one single machine learning framework. This can give us a more complete and realistic way to model the alloy behavior. So we designed two separate neural networks for this. One network process the chemical composition, and the other process the synthetic and processing conditions. Then we combine them together and predict the final property. This slide shows how we model the work. On the left side, you see how composition and processing data are going separately into two different neural networks, and their features are then merged to make property predictions. We have also added uncertainty estimations. This means for each prediction now we have confidence level, and this is especially helpful for guiding experimental work. Lastly, we looked at phase prediction based on chemical compositions. So we analyzed how each element affects the phase formation and quantifying their effect on either single or multi-phase promotion. So the figure on the left side, if the value is positive, that promotes the single phase. And if negative, it promotes the multi-phase formation. By using this analysis, we can intentionally design alloy with phase structure that we want. And as you can see, changing the amount of different elements that can change the phase in the alloy, either single or multi-phase. To summarize, we developed multi-scale machine learning framework for materials design. We applied probabilistic deep learning for accurate property predictions. And we also showed that combining chemistry, processing, and machine learning that can give us a powerful way to design advanced materials. And yeah, thank you everyone for listening. Thank you.
Any questions for a speaker?
Yeah.
I have a few questions. Can you hear me?
Yes, I can hear you, but it's a little bit slow.
Yeah, I can speak up. So for your first case study, the stacking fault values that you're using, are there experimentally measured values or are there computational?
Yes, those are experimentally measured values. The single element we are talking about, and all the values here in this figure you see, those are all experimentally measured stacking fault.
And is the model a purely data-driven model or is it physics-based?
I'm sorry?
Is your model, your data-driven model, is it purely based on data or is it like based on physics?
It's totally based on data-driven model.
And for your second case study, is your assumption that processing and chemistry independent, like input parameters essentially?
I didn't quite get the final questions. Sorry.
For your second case study, when you're looking at the effect of chemistry as well as processing, are you assuming those to be completely independent from each other?
Sorry, the last part. Can you repeat that?
So is your assumption for the second case study that processing and chemistry are independent parameters?
In some way, that is yes. And most of the studies, what they do, like they treat them separately, but we treat them together in one single framework. And I guess in some way they're related, not fully independent.
To what extent are they coupled? How do you do that?
How to quantify that?
So you say that they're not exactly independent, but how do you mean that? What are you doing?
We have not done that study yet, but so far what we have, I believe those are not independent. For example, let's say your processing condition for one material compared to other will be different. Niobium nitride or entropy alloy, those processing parameters are different. So I think those are related to each other.